Okay, it's 8:30, so let's go ahead and get started today. Good morning, everybody. Our first lecture after the midterm. So I want to ask just first, how's the midterm for everybody?
I felt the midterm pretty fair. Some problems, a little easier with respect to the homework, definitely.
That's good. That's good. Yeah, I definitely think that this exam was better than the first exam, at least in terms of difficulty. But it's good. So I haven't started grading those yet because I was trying to catch up on some other work. But I'm hopefully going to have those ready for you by Wednesday. But speaking of Wednesday, so Wednesday is a holiday, so we're not going to actually have any lecture on Wednesday. It's going to be Veterans Day, so nobody should have lectures on that day. So we're going to have just one lecture today, and then the next lecture is going to be on Monday of next week. Okay. So Wednesday, we're not going to have lecture, and I actually don't have any scheduled office hours on Wednesday either. But I'll be here, because I'm always here in my apartment. So if you want to set up a meeting and talk about anything, just let me know. So Wednesday, I'm basically free all day. So anytime would be good. Another thing, by Wednesday, I hope to have your next homework assignment ready for you guys to start working on. So it's going to cover a lot of what we're doing now and a little bit on pipe flow, which is what we're going to be starting next week. So you can expect that to be up by Wednesday as well. Okay. Besides that, are there any questions I can answer about just the maybe the midterm or just anything that we covered last week that we can get out of the way before we get started? Question? Sure. So question is, can I explain dependent and independent? So whenever you run an experiment, dynamic and kinematic viscosity. Yeah. So those are two kind of separate things. So the first thing is dependent and independent variables. So that's usually with regards to your experiment or even your analytical questions. You can put things in terms of dependent and independent variables. So your dependent variable is usually the variable that you're ultimately looking to solve for in your problem. So whether this be like an equation or an experiment or a simulation, so your dependent variable is what you want to solve for. So if we go back to the example from last week, our dependent variable on that pipe was the pressure drop, because that's the thing that we're interested in. And usually the independent variables are the ones that you usually have control over, or that you kind of know already ahead of time. So things like the viscosity of the flow, things like the density, things like the diameter of the pipe. So these are variables that you know their values beforehand. And so that's why they're called independent, because their values are independent of basically anything else that you do in the experiment. Whereas the dependent variable, their value is going to depend on the values of all the other variables. That's kind of where they get their naming convention from. Okay. And so this terminology is actually used mostly for experiments, because a lot of times, when you run an experiment, you have control over certain variables, right? Like you run an experiment on a pipe of a certain size, so you have control over the size of the pipe. You have control over the type of fluid that you're going to use. So you have control over the viscosity and the density. And in the case for last week, you have control over the velocity too. So maybe you have control over the pump, that's running the flow. And so that's kind of another reason why we call that independent variable. Yeah. Okay. And so the difference between dynamic and kinematic viscosity. So they're just different forms of viscosity. And so viscosity, whether you have dynamic or kinematic forms, they represent the same thing. So they represent the fluid's resistance to flow. And so dynamic and kinematic, they just kind of represent the same things in just different units. And so an analogy that I like to draw is with density and specific weight, right? Or actually even just mass and weight in general, right? And so both of them kind of represent, of course, they're different. A weight is a force and a mass is a mass. But when you're using them to talk about how massive an object is, or how much it's going to weigh, you can use kind of both interchangeably, with just kind of the understanding that you use the acceleration due to gravity in order to kind of switch in between them. But the idea that they represent is kind of the same thing. So the dynamic and kinematic viscosity is kind of the same thing, where they both represent the same idea. It's just that their units are different depending on if you factor in the density or not. Yeah. Does that answer your question? Okay. All right. Any other questions before we get started today? Okay. All right, so let's pick it up where we left off last Monday. So last Monday, we had just finished talking about the method of repeating variables. Okay? And just to kind of refresh your memory, we use this method along with the Buckingham pi theorem in order to derive these dimensionless groups. Okay? And so these dimensionless groups, just like their name implies, they're combinations of variables in a system that are rendered dimensionless. And by dimensionless, we literally mean that they have no dimensions. So we like these a lot because they really simplify the analysis, and they let us do a lot of interesting things with the experiment. So you'll see a lot of the applications for dimensionless variables today. But first thing I want to do is I want to run through another example for the method of repeating variables, because it's a fairly long method, 7 steps. So I think it's useful to kind of run through another example just so you can kind of see the entire process from start to finish again. Okay, and so in this example, let's consider a rectangular plate. Okay, I'm going to draw it in 3D. Right, and then to this rectangular plate, we're going to hit it with a jet of fluid. Okay, so let me use blue. Okay. Right, so we have fluid that's kind of hitting at it just like this. Okay. And because the plate is in the way, the fluid is going to kind of, arc around it. And we have kind of a wake region right here. Okay, so let's define the variables that that are in this flow. Okay, and so for the fluid itself, the fluid has a velocity, and so that's going to be given by v. Okay, it has a dynamic viscosity, so that's mu. It also has a density, rho. Okay. And so those are the 3 variables that we know for the fluid. Okay. And we also know the dimensions of the plate. Okay. So it's going to have a width w and a height h. Okay. All right. So what we're interested in solving for is what is the drag force. Okay. And so we'll call that F sub d on the plate. Because as this wind hits the plate, there's going to be a force that kind of pulls the plate into this direction. Okay. And we want to run an experiment, or at least we want to determine what that drag force is. Okay. Right. And so we're not actually going to solve for that drag force, but what we're interested in is finding out, what are the dimensionless variables that this drag force depends on. And then we're going to use our method of repeating variables in order to determine that. Okay. Okay, so the first step in the method of repeating variables is to list out all the relevant variables. Okay? So that was step 1. Right. So remember, normally step 1, this is the hardest step to do in just kind of a given situation. But for this one, all the variables are kind of listed out there. Okay. Okay. And so let's put this in the form of dependent variables and independent variables. Okay. And so our dependent variable, or the one that we're solving for in this case, is f sub d. Okay, so let's put that on the left-hand side of the equal sign. Okay. And then this is going to be a function of all of our independent variables. Okay. So remember, this little f right here means function of, so it's not a variable in itself. It's just said that this fd, which is our dependent variable, is going to depend on all of our independent variables. Okay. And so we have the width of the plate, the height of the plate, we have the velocity of the fluid, we have the viscosity, and we have the density. Okay. All right. And so that's step 1. So step 1 in this case, is simple, just because I've kind of listed out all the variables for you. But if you're applying this method elsewhere, this you kind of have to be careful with this part. And last time, remember we talked about a lot of methods that you can use to determine this list of variables. Okay. Okay, any questions on this? Okay. Okay, so let's continue on with the method of repeating variables. So step 2 of this is that we need to list out all the dimensions for the variables. Okay. And so remember, you can either use the MLT dimension set, which is mass, length, and time, or you can use FLT, which is force, length, and time. Okay, so you can use either one, and so it doesn't matter. So for this problem, I'm going to use MLT just because that's the one I feel more comfortable with. But you should just use the one that that you want. Okay. Okay. So first we have FD, which is our drag force, and so the dimensions for this could be mass over length times length over time squared. Okay. Next we have the two dimensions for the the height and the width of the plate, and so both of these have a dimension length. Okay. Next we have the dimensions for the velocity, so this is length over time. Okay. Next we have the dimensions for the dynamic viscosity, and so this is m over lt. And then finally, we have the dimensions of the density, which is mass over length cubed. Okay. Okay. And so for those, remember for step 2, all you have to do is just write out the dimensions. So you can either look up just some common units for these quantities and derive the dimensions from that, or you can go off. Remember we had that kind of big table from the first week. Okay. Okay, and so step 3, so now that we have the dimensions, step 3 is to determine how many dimensionless variables do we need. Okay. Right, and remember the another name for the dimensionless variables is called the pi terms. Okay. Named after the Buckingham pi theorem, which is what we're using here. All right, and so for that, let's use our Buckingham pi. And so remember, our number of pi terms is going to be k minus r. Okay. So remember, k right here. This is the number of variables in our system. Okay. Okay. And r right here. This is the number of basic dimensions represented. Okay, and so let's determine k. And so for k, all we got to do is just count up the variables. We have 1, 2, 3, 4, 5, 6. Okay, so our k is going to be 6. And for the dimensions represented, we're going to count up how many of mass, length, and time are actually represented. Okay, and so we can see that we have a mass, we have a length, and we have a time. Okay, and so r here is going to be 3. Okay. And so we do the simple arithmetic, 6 minus 3, and what we get is 3 pi terms. Okay. So it's a little bit, it's going to be a little bit more work than our previous example, because last time we only had to solve for 2 pi terms, but this time we're going to solve for 3. Okay. It's a little bit more work, but it's you'll see that one of them is actually really, really simple. Okay. Okay. Any questions on this? Okay. Okay, so let's do step 4. Okay, and so step 4, oh, question? Sure. So how do I, so the question is, how do I determine R? And so how I determined R was to count how many basic dimensions are represented, okay? And so our basic dimension in this case is M, L, and T, right? So those are kind of like our primary colors for this problem. Okay, and so the way that the way I determine R is I kind of think of this as kind of like a check mark, right? And so I basically look at our list of dimensions right here, and I see which one of these there has to, if there's at least one mass in here, then we can kind of put a check mark there. Okay, and so what I've circled here in orange is that for this one, you can see that we have one mass, and so mass is present, so we'll put a check mark there. Okay. For L, we see that we have at least one L here. I mean, L shows up many times, but there's one instance. Okay, and so there's our L is there, and then time we can see that we have a time in our velocity term. And so we can put a check mark there. And so we can see here that all three basic dimensions, mass, length, and time, are represented in our variable. So our R is going to be 3 because that's all three basic dimensions. Yep. Okay. All right. So step 4 is to choose our repeating variables. Okay. Okay. And so remember what our repeating variables are. So our repeating variables are going to participate in multiple different dimensionless groups. Okay. And so remember the kind of the rule of thumb for the repeating variables. First of all, we know we have to pick 3 of them because we have an R value of 3. Okay. Okay. Right. And so since these guys are going to take place in multiple groups, what we want them to be is we want them to be the simplest representations of the dimensions. Okay. Okay. And so the way that I do this is I basically write down our 3 dimensions here. Okay. So we have mass, length, and time. Okay. And then what I do is I look back at the variable list and I say, what is the variable that has the simplest representation of mass? Okay. And so simple usually is defined by, there's less other stuff in there. Okay. And there's not too many things. Okay. So let's look at mass first. Okay. All right. And so let's look at all our terms here that include mass. So we have our FD. Okay. We have our mu, which is our density, and we have our mu, which is our viscosity, sorry, and we have our rho here, which is density. Okay. And so all of these guys, none of these make great candidates for mass because ideally we'd want something with just mass by itself, but all of these guys have mass in there somewhere. Okay. And so looking at these, we have to find out what's the most simple, where's the place where mass is represented most simply. Okay. And so let's first look at FD and mu, which are density. Okay. And so these guys are actually pretty complicated because they have all 3 mass, length, and time. Okay, so force is a mass times length divided by time squared, and our viscosity is mass over length times time. Okay, and so neither of these guys would make good candidates because they have everything going on there. And so even though we have a length cube here, actually the simplest representation for mass is going to be the density because it just has only 2 out of the 3 dimensions, right? And so we have only mass and length, but not time. Okay, and so the simplest representation for mass is actually going to be our density. Okay. Okay, so now let's look at length. So we have options here. So length is usually the simplest one to satisfy to get a simple representation. And let's look at our dimensions for the width and the height. Okay, and so both of these guys have just dimensions of simply length. And so this is perfect. So this is exactly what you want from a repeating variable because it's a very simple representation. Okay. But there's 2 of them, so you can choose them however you want. So either one is fine. But for this one, I'm going to pick width. But it's really a coin flip. So you can, since both of them have the exact same dimensions, you can choose either width or the height. Okay. Okay. And so now let's look at time. And so we have kind of a similar thing here. We have 3 different variables that represent time. And so the first thing is we have the force, then we have viscosity, and we have the velocity here. Okay. And so using the same logic that we had with the mass, we're going to choose the velocity here to represent time because it's relatively the simplest, okay? Because velocity is just length over time, so time just shows up just once and there's no mass, so there's a lot less to deal with, okay? Because if we chose the force or the viscosity here to represent time, then we have a lot of other stuff going on, and it's going to make our computations more difficult down the line. Okay, and so for time, I'm going to choose velocity. Okay, and so this here is density. This is width, and this is velocity. Okay, right. And so generally when you're picking your repeating variables, you want to choose the simple ones because that saves you more work down the line. But with that said, you know, you could do this problem, you know, making you know, some of the others repeating variables too. Okay, it's just going to make things a bit more complicated. So the only thing that you can't do is that you can't choose your dependent variable as your repeating variable. Okay? Right? Because then that wouldn't make sense. Because remember, the what we're solving for in this problem, or what we're interested in, is the force, and so it wouldn't make any sense for force to show up on kind of both sides of the equal sign, because that's what we're solving for. Okay, and so besides this rule right here, you know, there's really no restrictions on what you can pick for your repeating variables. It's just that, you know, choosing simple ones will just make your life a lot easier down the road. But you can do the problems just fine, you know, with the other ones. So you can choose viscosity here for one of them if you really want, but it's just going to be a bit more complicated. Okay. All right. Any questions on how we chose the repeating variables? Okay. Okay, so now that we have the repeating variables, we have the non-repeating variables. Step 5 is to actually solve for the dimensionless groups. Okay, and remember for this, we're going to form this this kind of linear system here. Okay, and so we need to do this 3 times because we have 3 non-repeating variables. Okay. Okay, and so let's start with the drag force. Okay. Okay. And so our dimensionless group involving the drag force is going to be F times D multiplied by our density, or let's start with the width actually. So let's start with the width. Okay. And we're going to raise that to the A power. Okay. Next we have our density, which we're going to raise to the B power. Okay. Then we have our velocity here, which we're going to raise to the C. Okay. And so remember, what we need to solve for is we want to solve for these coefficients here, or these exponents, A, B, and C, that makes this quantity dimensionless. Okay. Okay. And remember, the way that we did that was we put everything here in terms of its basic dimensions, and then we form a 3x3, you know, linear system. Okay. Okay. All right. So first, let's do the force. The force is going to be mass times length all over time squared. Okay. Next, we have the dimensions of the width, which is just length. Okay. We're going to raise that to the A power. Next, we have the dimensions for density, and so that's going to be mass over length cubed raised to the B power. Okay. Next, we have the dimensions for the velocity, which is length over time raised to the C power. Okay. And so now what we're going to do is we're going to form an equation for each of the dimensions. Okay. And so first we have our mass equation. Okay. And so what we need to do now is we need to sum up all the contributions to the mass from these variables. Okay. And so first thing that we notice is that our FD will contribute a 1 mass here. Okay. Because we have mass in the numerator for FD. Okay. And that's raised to the first power. So that's a 1 for mass. Okay. Our next contribution for the mass comes from our density. Okay. And so our density just has a single mass on top And so this can be a plus b, okay? And this is going to be equal to 0, right? And so we can actually solve this equation outright, and we say that b has to be equal to -1. Okay. Okay. Next, we have our length equation. Okay. And so this one's going to be the most complicated. So we're going to have 1 plus a minus 3b plus c. Okay. So all I'm doing is collecting all the powers of length, across our expression here, because we have a power of 1 from FD, we have a power of a from the width, we have a power of -3 from the density, and we have a power of 1 or power of c from the velocity. Okay, and all this has to equal 0, right? So we can't solve that one yet because we don't have enough, and so let's write out our equation for the time. Okay, and so for time we're going to have -1. From the or -2, sorry, -2 from the force, okay? And then we have minus c. Okay? And so from this equation, we see that c is equal to -2. Okay, and we plug those into the middle equation, and we get that a is also equal to -2. Okay. Yes. Okay. Okay. Any questions on this? Okay. And so now that we've solved for these coefficients or these exponents, we can form our first dimensionless variable. Okay. And so our first dimensionless variable is going to be pi1. Okay. It's going to be our force, which is FD. Okay. And then we're going to multiply that by all of our repeating variables. Okay. So first we have density, which is raised to the -1 power. Then we have our velocity, which is raised to the -2. And then we have our width, which is raised to the -2 power. Okay. Okay. And so now we just have to repeat this process, for all the other non-repeating variables. Okay. And so our second one is going to be our viscosity. Okay. And so we're going to set up the same system. Oops, I skipped a step. So this should be the density here, and this should be velocity. Okay. And so now we're going to form the same system, for this guy. Okay. So we're going to put these in terms of the basic dimensions. We're going to form the linear system and then solve for the equations. Okay. So just to make sure that we kind of have enough time to, for all the stuff at the end today, I'm just going to skip ahead to the system. But to get from here to here, I basically just put all the variables in terms of their dimensions. Okay. And so we solve the system. We get b is equal to -1. We get a is equal to -1, and c is equal to -1. Okay. And so we can form our second pi term, which is going to be mu over w rho v. Okay. And so that's our second pi term. Okay. Okay. So basically, this is just the process that you kind of follow for this. But for our last pi term, we can actually take a shortcut because it's a relatively simple term. But before we do that, are there any questions on this page right here?
Yeah, once again, just to reiterate, for the selection of the 3 variables, we chose we chose width, rho, and velocity in that certain order based on the ease of the repeating variables.
Yes, yeah. So you want to choose variables that are simple, but you want to make sure that you have all 3 mass, length, and time represented in your repeating variables.
Right.
And so if you pick like width, height, and velocity, so those are, I think, the 3 simplest ones because you have length and length and length over time. That wouldn't work because you don't have mass among your repeating variables. You want to make sure that you have at least one of every dimension in there. Yeah, and then pick the simplest forms for those.
Okay. And then does it matter how we decide to? Oh well, yeah, yeah. That's basically what you just said. Okay.
Mhm. Okay, and so another question, can I show how I form the pi equations after solving for B and C? Yeah, sure. And so after solving for B and C, A, B, and C, basically what I'm going to do is plug all of these guys in for their expressions right here. Okay? And so for B, we're going to plug in a -1 here, and for A, I'm going to plug in a -1 here, and then for C, I'm going to plug in a -1 right there. And so when you raise these quantities to a minus, remember, a minus exponent means you take the inverse of that. And so W to the -1 power means you do 1 over W. A rho to the -1 power means we do 1 over rho. And then V to the -1 power means we do 1 over V. And so that's why all these terms end up in the denominator right here with a power of 1, because their exponent was -1. Yeah. Mm-hmm. Okay. And so our last repeating variable in here was the height. Okay. Okay. And so our height here just simply has dimensions of L. Okay. And so all we need to do here is we need to just cancel out this dimensions for L. Okay. I said divide by a repeating variable to cancel this. Okay. Okay. But in this case, it's actually pretty simple, because remember, one of our repeating variables was W, okay, which also had dimensions of L. Okay. And so we can just kind of see, so you can definitely just you can definitely write out the whole equation just like you did before. But for this case, you don't have to kind of go through that whole thing. You can kind of just simply say that we have H, which has dimensions of length. We have W, which has dimensions of length. And so all we got to do is just take the ratio in between them in order to get our last dimensionless one. And so from here, we call it by inspection, we say that pi 3 is equal to H over W. And so if it's a simple case where you can determine just by looking at it, then you can just kind of skip the whole steps. And so I know what everyone's thinking. So on the homeworks, I know I give you the solutions for this. And so if you're doing this in the homeworks and you say by inspection of the homework solutions, this is what the dimensionless group is, obviously I'm not going to give you credit for that. So it's only for, the really simple ones, that you can do this inspection method. Because obviously, on an exam, you're not going to have the solutions there for you. And in real life, you're not going to have the solutions there for you too. So only for the cases where you basically just have one, the non-repeating variable just has one dimension, and you can just cancel it out just by dividing. That's okay. But for everything else, I want you to actually write out the full system. Okay. Okay. And so now that we have all three dimensionless variables, we can finally form our system. Okay. Okay. And so our system is going to consist of our three dimensionless variables, put into a relationship, the relationship status. Okay. And so our first dimensionless variable, this one involves our dependent variable, and so this is going to be FD over rho times velocity squared times width squared. Okay. And so this is going to be equal to phi. Okay. Remember, phi here just represents some function. Okay. Okay. And so we don't know what that function is. And so usually, we have to run the experiments in order to do this. Okay. And so this is going to be a function of our second pi term, which is our viscosity over W rho V. Okay. And then finally, we have our third pi term, which is H over W. Okay. And so this is kind of the final relationship that you have right here. Okay. And so another name for the H over W right there that you might be familiar with is called the aspect ratio. So it's just the ratio of the width and the height of the plate. Okay. All right. And so that's another example just to show you, the method of repeating variables. So it's, it's usually, it's not the most difficult thing, but you kind of have to make sure you're careful at every step, and you kind of do every single step there. Okay. Okay. Any final questions on the method of repeating variables?
Yeah, can you explain once again how you got the third pi term? So it's just the height divided by the width?
Yeah, yeah. So remember, for these, all these pi terms, they have to be dimensionless, right? And the way that they become dimensionless is because, you know, you take some combination of the repeating variables. And so in the third pi terms case, since it's just height, you know, that's just this just has dimensions of length. We just have to cancel that out with another dimension of length. So that's kind of what we did for that.
Okay.
Mhm. Right. So the way that you kind of form this relationship is you have one of the pi terms on the left-hand side. And remember, the pi term on the left-hand side, that's the one that involves your dependent variable. And so since our dependent variable in this case was the force, and so our pi term that involves the force, that's going to be on the left-hand side, and then all the other pi terms that are, you know, everything else, those are going to be on the right-hand side. Yeah. Mhm. Yep. Okay. And so that's kind of the method of how you derive these dimensionless groups. Now let's talk about some dimensionless groups that show up pretty often in fluid mechanics. All right. And so because fluids, they all follow kind of the same equations, and they all depend on very similar variables. You know, there's certain groups that show up, you know, pretty often. Okay. Um, they're chopping down a tree outside my apartment. And so some of these are actually going to be really important. So actually, some of these, you know, we'll actually see later on, you know, in the class. You know, as we go over things like compressible flow and turbulence, actually. And so the thing I want you to remember with these dimensionless groups is that, you know, yes, these numbers don't have any dimensions, but just because they don't have dimensions doesn't mean that they're meaningless. Okay. And so what you'll notice from these dimensionless groups is that these dimensionless groups often represent a ratio of some kind. Okay? And so a ratio, you can think of it as a balance in between, you know, something on top and something on the bottom. And so depending on what that ratio is, you know, you're going to observe different behaviors in your fluids. Okay. And so let's jump into the first one, just so you can kind of show, just so I can show you what I mean. Okay. And so the first one is probably the most important non-dimensional parameter in fluids. Okay. And so we've actually seen this. It actually appeared in both of our examples so far. And so our first dimensionless variable is going to be the Reynolds number. Okay. And so the formula for the Reynolds number, and so we give it the symbol Re for Reynolds. Okay. And it's going to be the ratio of the density times the velocity times the length all over the viscosity. Okay. 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 And so what does the Reynolds number represent? And so even though this guy is dimensionless right here, remember this represents a ratio. Okay? And so the ratio that it represents is the ratio of inertia forces okay, and viscous forces. Okay? Okay. And so inertia forces, you can kind of think of it as like, you know, the force that's associated with motion, right? And so if you have like a fluid that's moving forward, or even just like a solid object that's, you know, moving forward with some velocity, you know, it's going to have some inertia to it. Okay. And so inertia, you can kind of think of that as the force or the energy that's associated with fluid motion. Okay. And viscous forces, that's the forces that are associated with viscosity. Okay. And so those are going to be like your viscous shear forces that kind of prevent motion. Okay. And so this Reynolds number kind of represents a ratio of these two guys. Okay? And so, you know, the Reynolds number is actually really important for a lot of fluid mechanics. And so what we'll find later on is that if you have a really low Reynolds number, so Reynolds number is, you know, very, very low. Okay. And this, in these cases, viscous forces will dominate. Okay. And in the limit that viscous forces dominate, you know, that lets you make certain assumptions about your equations, and you get some certain kinds of behavior. And then for the other side, if Reynolds number is very, very large, if Reynolds number is really, really big, then what we say is inertial forces will dominate. Okay. And so the force of the motion of the fluid will basically overcome any kind of viscous forces. Okay. And what actually tends to happen here at really high Reynolds number is that the flow actually becomes pretty chaotic because there's so much inertia in the flow and there's no viscosity that's really holding it back. And so you really get a lot of chaotic flow patterns. And so this is actually a very, a case that you probably have experienced at some point if you've flown on a plane. And so if you have very high Reynolds number, this is known as turbulence, okay? And so turbulent flow tends to be, you know, like you've probably sat on a plane with turbulence before. It tends to be very chaotic, you know, very unpredictable, and can do a lot of really crazy things, okay? And so, you know, the way that we determine, you know, whether a flow is turbulent or not is to measure the Reynolds number. Okay? So Reynolds number, you know, it's seen basically everywhere in fluid mechanics because you always have this kind of competing or competition in between inertia forces and viscous forces in whatever fluid that you consider. Okay. Okay. Any questions on this?
Yeah, your notation for RE is less than and RE is greater than. Is that 1 or an I or
It's
an
a 1. Yeah.
Okay.
Yeah. Yeah. So I use 1 as kind of a reference point. So if RE is much less than 1, then it's, you know, it's a very small Reynolds number.
Okay.
But if RE is really big, so usually Reynolds number can get into like, you know, the hundreds of thousands or the millions even. That's a very large Reynolds number. So that's
Okay.
when you get turbulence.
Thank you.
Right. Any other questions on this? As the chainsaw starts up again. Okay. And so that's the Reynolds number. So that's probably the most important one. Then I have another one in the notes called the Freud number. Right. So this one's not as common, but it still exists. Okay. So FR is velocity divided by gravity times length. Okay. And what this represents is the ratio of inertial forces over gravity forces. Okay. Okay. And so, you know, if you have any kind of verticality to your flow, like you have a waterfall or something like that, or flow, you know, going down a vertical pipe, you know, the Freud number can be relevant there, but a lot of times it's usually not that that relevant. But I picked it just because it's relatively simple to interpret. Okay? But the last one that I want to go over, this one you've probably heard of before, and so this is the Mach number. Okay? And so Mach number, the way that we denote it is MA. Okay? It's simply just a ratio of V, which is the velocity of the fluid, okay, over C. Okay? Where C right here, this is the speed of sound. Okay? And so this is a ratio, again, of inertial effects, okay, or inertial forces. Okay? And on the bottom here, we have compressibility effects. Okay. Right. And so this is really important if you're going to be looking at, you know, supersonic flow. And so, you know, you talk about airplanes that fly at really high speeds and stuff like that. Okay? And so, you know, we haven't really talked about the speed of sound because, you know, all the fluids that we've been talking about so far, remember, are incompressible. Okay? And so incompressible fluids, you know, they don't have to be, you know, we don't consider that the density can change. And the reason for you to do that is because most of the times, you know, you don't see compressibility effects until you reach really, really high speeds. And most of the times, you know, we don't get up to those, at least for the problems that we do. Okay? But I know there's a lot of interest in this. So, you know, at the end of the class, I am going to kind of do a very brief introduction to compressible flow. At least that's the plan for now. Okay. Okay. And so, you know, these are just some dimensionless groups that are, you know, relevant for fluids. But, you know, remember, this idea of dimensionless groups is not limited to fluids. So other fields will also have their own dimensionless variables to worry about. Okay. But these are kind of three that kind of show up relatively often. At least the Reynolds number shows up a lot. Mach number shows up if you're talking about compressible flow. Freud number, honestly, I haven't used it, but it's you know, if you have gravitational flow, then it'll show up there. Okay. Okay. Any questions on these? Okay. All right. So now let's talk about some more applications for these dimensionless groups. Okay. And so the first application I want to talk about is how do we use dimensionless groups with experimental data? Okay. Because the way that we use these is you know, going to be important for this. Okay. And so I'm going to go over kind of two different situations here. And so first, let's go over a situation where we only have a single pi term. Okay. Okay. And so an example for this, you know, could be a drag force on a particle or on a sphere, I should say. Okay. And so for this, we have a sphere. We have fluid that's going over it. Okay. And so this fluid has a velocity and a viscosity. Okay. And the sphere also has a diameter. Okay. And then what we're interested in here is the drag force. We have Fd. Okay. And so this Fd is going to be equal to a function of diameter, velocity, and viscosity. Okay. And so the density is missing here because it's going to be a steady flow. Okay. And so by you know, if we take, you know, because we only have 4 variables here, okay, and our r here is 3 because we have all mass, length, and time represented. Okay. So in this situation, we only have 1 pi term. Okay. And so we have pi 1. Okay. And so if you run through the method of repeating variables, what you find is that pi 1 is equal to Fd over V mu d. Okay. Right. And so in this situation, we only have a single pi term. Okay. And so in these cases where you only have 1 pi terms, you know, this is actually really convenient because this pi term basically has to be constant for the flow. Okay. Okay. And so we'll call that constant C. Okay. And so this is nice because what this tells us is that, you know, we can find, if we find out what this constant C is, then we can use this relationship to find out, you know, basically any other flow configuration. Okay. And so basically, you know, in these cases, which only have 1 pi term, we can basically just run one experiment, measure the drag force under a certain velocity and viscosity, okay? And then from there, we'll be able to find the drag force under any other, you know, similar configuration. So on like a bigger sphere or a higher velocity or a different fluid. Okay, and I'll show you kind of how to do that on the next page. Okay, right. Are there any questions on this? Okay. Okay, and so let's say that we ran an experiment and we found that the drag force is equal to some number. Okay, and so I'll call this number B. Okay, with well, actually I'll call this F naught. Okay, because we know it. Okay, and this was run under the following situation. So let's say that we have a diameter of D naught. Okay, and then we have a velocity of V naught, and we had a viscosity of mu naught. Okay, and so our constant C in this case will be F naught over D naught, V naught, mu naught. Okay. And so let's say that, let's take these results and let's say that, okay, if we increase our velocity to a second amount, okay, and we want to solve for the drag force on the sphere. Okay. And so let's form our relationship again. So let's say that we have FD is equal to or over D, V, and mu. Okay. Okay. And so because our system here has only one dimensionless variable, we've already solved for C. So we can take this and plug this in here. Okay. And then we can now solve for the new FD with these new variables here. Okay. So a new FD is going to be equal to C times D, V, mu. Okay. Where these guys are going to be the configurations of the new experiment. Okay. And then with that, we can solve for the FD without having to run a whole nother experiment. Okay. And so for cases where you have a single pi term, this is actually really convenient because you just have to run the experiment once, and then everything else, kind of falls into place based on that one experiment because of what you did with the dimensionless variables. All right. Any questions on this? Okay. Okay, and so that's the case with one pi term. And so now let's go over the more common case with 2 pi terms. Okay. And so for 2 pi terms, the relationship is a little bit more complicated because now we have a functional relationship. Okay. So we have something that looks like this, right? So we have pi 1 is equal to some function of pi 2, where this we don't know. Okay. Okay. And so for these situations, you actually have to run, several experiments to get data. Okay. But then the way that you present the results is that you graph one, dimensionless group against the other one. Okay. And so let's do it like this. Okay. And so we have a graph right here, right? And so how you put these variables is really important. So on the y-axis for this graph, you want to put your dependent variable. And so our dependent variable in this case is going to be pi 1 because it's on the left-hand side of the equal sign. Okay. And then our independent variable here is going to go on the x-axis, and so that's going to be pi 2. Okay. And so what we want to do is we want to run the experiment and get these data points. Okay. Right, so let's say that we ran the experiment and we got data points that look like this. And so these data points were from experiments. Okay. And so once you have the data from the experiments, then you can kind of plot the relationship like this. Okay. And so this is nice because this is, this curve that we get right here, we call this curve, universal. Okay. And so if we kind of come up with a similar situation, which has the same pi terms, then we can actually use this graph to predict the results. Okay. And so even though we have two pi terms and it's not as simple as just solving for a constant, we can still use this information to, to extrapolate to kind of future situations without having to run, new experiments. So, remember, the point of these dimensionless variables is so that, you can run, a relatively small amount of experiments and to have those results kind of extrapolate to a lot of other situations. Okay. Right. Any questions on this? Okay. Okay, and so the last thing that I want to go over is this idea of modeling and similitude. Okay. Oops. Okay. And so to motivate this, let's go back to kind of a situation that that was presented at the beginning of this unit. Okay. And so let's say that you work for an aerospace company, and so say it's Lockheed or Boeing or Raytheon or anything over there. Okay. And you want to test out your new airplane wing design. Okay. And so if you ever stood next to an airplane, you know that the airplane is enormous, right? Like especially if you're talking about a commercial airplane, right? And so if you want to test out your airplane wing, and you want to run an experiment on it, normally that would require you to build a full-size airplane wing, which is extremely expensive, and then you got to find a wind tunnel that's big enough to fit your airplane wing. So so those exist, so they do have ginormous wind tunnels, and they're actually really cool. So if you ever get the chance, you should definitely check it out. But as you can imagine, running this experiment would be really, really costly. Okay. And so a lot of times, if you want to run an experiment on, something that's really big, a lot of times it's just not economically practical. Okay. And so you have objects that are too big, and you also have objects that are too small too, right? So if you want to test out a medical device that's going to be micro size, and so conducting an experiment over something that's really small is also really expensive because you need really sensitive machines to do that too. Okay. Okay. And so the key word here is practicality. And so you definitely can run experiments on these, and there's equipment that exists. Just a lot of times it's just not practical. Okay. Okay. And so I'm going to throw a little bit of terminology at you guys. So let's say that in this case, the full scale object, okay, whether it be an airplane wing or a tiny device, okay. And so the full scale object that we want to run the experiment on, we'll call this the prototype. Okay. Okay. And so we don't want to run an experiment on the prototype just because it's not practical. Okay. But what we want to do is we want to run an experiment on an object that's a more practical size. Okay. Okay. And so this more practical object, which will be something that's more reasonably sized. Most of the time, it's something that can relatively human sized. We'll call this the model. Okay. Okay. And so what we want to do is we want to run an experiment on the model, but then we want the results to be applicable to the prototype. Okay. And so how do we make it so that, you know, whatever we obtained from the experiments on a model, that we can apply that to the prototype, okay? And so, you know, we can do this if we make use of our dimensionless groups, okay? And so if we frame our experiment in terms of these dimensionless groups, then we can kind of, you know, extrapolate the results upwards, okay? Okay. And so if we design our experiments in such a way that the values of the dimensionless groups, they match that of the full-scale prototype, then we can take those results and apply them on the prototype, okay? And so we're going to make sure things like the Reynolds number, the Mach number, you know, any other dimensionless groups, aspect ratio, you know, they're going to match up, okay? And I'll show you an example of, you know, how we do that on the next page. But before we do that, are there any questions on this? Okay. Okay, so let's do an example. And so let's take the example that we did before, which is the drag force on a rectangular plate. Okay, so let me draw it again for you here. So this is the example that we did at the beginning of class today. Okay. And so from that problem, what we found was that, you know, we had FD over rho W squared V squared. Okay. This is equal to some function of the viscosity over rho VW, and then comma W H over W. And so just a bit of trivia, you know, before we get started, this quantity right here is 1 over the Reynolds number, okay? And so actually, you know, it's even though we have the viscosity here in the numerator, a lot of times it's standard to kind of put the Reynolds number in its proper orientation. And so we can say that we have this is equal to FD over rho W squared V squared is equal to some function of rho VW over mu over H over W. And so all I did there was I just flipped the Reynolds number just to put it in its usual orientation. So that's usually just fine. Okay. Okay. And so let's say that, you know, you work for a you actually work for Cal State Fullerton, and, you know, Cal State Fullerton has been putting up those billboards on the side of the 57. Okay. And so let's say that we want to find the drag force, you know, of Santa Ana winds hitting our billboard. Okay. And so the dimensions of our billboard look like this. So let's say it has a height, we'll call this HO, of 20 feet, okay, and has a width of 35 feet, okay? Right. And so that's obviously way too big for us to run an experiment on, because that's not even going to fit through the door, okay? And so let's use dimensionless variables to design an experiment on a plate with a max height of 5. And so we're going to, instead of a height of 20 feet, we're going to have a height of 5 feet, and we need to adjust the values of all the other parameters in order to make this work. Okay. Okay. Any questions on that? Right. And so in this case, you know, we're scaling down our full-scale prototype into a much smaller model, you know, just so that we can actually practically run the experiment, you know, in something that will fit inside the door. Okay. Okay. And so what we want to do is solve for all the other variables that will make this experiment work. Okay. Okay. And so let's start with our aspect ratio. Okay. So remember, our aspect ratio is just simply the ratio of h over w, okay? And so this has to be the same for both the model and the prototype. Okay. And so this this quantity right here, actually in my notes I have w over h, and so it's the same thing. Okay. And so if we do this for the full model, we say that w over h is 35 over 20, and so this is going to be 1.75. Okay. And so this has to be the same for our model. Okay. Okay. And so what we want to do here is we want to solve for the width of our model. Okay. Okay. And so we know for our model here, our h has to be 5 feet. Okay. And we know from the full prototype that the ratio of w over h has to be 1.75. Okay. And so we can basically solve this equation for w. And so w is going to be equal to 1.75 times 5 feet. Okay. And this is going to be 8.75 feet. Okay. Right. And so in order to make sure that our our plate here has the same ratio of height and height and width, if we have a maximum height of 5 feet, then the width has to be 8.75 feet. So it's still pretty big, but at least it's smaller than 35 feet, which is massive. Okay. Okay. Any questions on this? Okay. And so that's the first dimensionless variable. Okay. And so we've taken this dimensionless variable here, and we found kind of the matching value for w that will satisfy this. Okay. And so now let's look at the second dimensionless variable here, which is our Reynolds number. Okay. And so let's say that our billboard will be exposed to Santa Ana winds. Okay. And let's say that the Santa Ana winds will vary from 10 miles per hour to 60 miles per hour. Right. And so what we want to do is we want to solve for the velocity of the air in our experiment. Okay. Okay. And so we can set it up exactly the same way as our our aspect ratio. Okay. And so what we need to do is we need to equate the Reynolds number for the prototype equal to the Reynolds number for our model. Okay. And so let's plug in for the Reynolds number here. So we have rho times velocity times width all over viscosity. Okay. And we have the same quantities for the model. Okay. So we have rho m, Vm, Wm, and mu m. Okay. Okay. And so we've already solved for what W needs to be. Okay. And so we go ahead and plug those in just fine. Okay. Another thing that we can cancel out here is the density on both sides. Okay. And so in this case, we're just going to use just standard, atmospheric air. And so atmospheric air is going to have the same density. Okay. And so since we're using the same air for our experiment as for our prototype, we can say that these densities are going to be the same. So they can cancel out here. Okay. And the same for the viscosity. Okay. And so since we're using the exact same fluid, the density and the viscosity will cancel out, okay? And so now that we've made these simplifications, we can solve for Vm, which is the velocity in our experiment, okay? Okay, any question on this? Okay. Okay, and so we see that Vm is going to be equal to V in the model, or V in the prototype, times the ratio of the width in the prototype over the width in the model. Okay, and we know that this ratio right here is going to be 35 over 8.75, okay, which is equal to 4. Okay, and so what this tells us is that our velocity in our experiment has to be 4 times that as our prototype in order to get the same results. Okay. And so in the prototype, remember we're considering Santa Ana winds. Okay. And so the winds are going to be 10 miles per hour to 60 miles per hour. Okay. And so in our experiment, or our model, it has to be 4 times this. And so 10 times 4 is going to be 40 miles per hour. And then 60 times 4 is going to be 240 miles per hour. Okay. Okay. And so, with those, if we increase the velocity by that much, we'll be able to match the same Reynolds number as our prototype, and that'll be able to allow us to relate the results from one side to the other side. Okay. Okay. Any questions on this? Okay. Okay. And so now that we've solved for basically all the parameters in our model, now the next thing is just to simply run the experiments and present the results. Okay. Okay. Right. And so in this particular case, we're gonna follow the procedure for a 2 pi term system. Okay. Okay. So even though we have 3 pi terms here, we have the drag force, we have the Reynolds number, and we have the aspect ratio. The aspect ratio is just going to be kind of fixed here, so we're not going to worry about it. And so we just have kind of the relationship between the pi term involving the drag force and the Reynolds number. Okay. And so let's plot those two results, against each other. And so let's say that you ran your experiment, and the way that you're going to present the results is going to look like this. Okay? So remember, for a 2 pi term system, on the x-axis here, you're going to have your independent pi term. Okay? Okay. Which in this case is the Reynolds number. And so we have Reynolds number equal to rho VW over mu. Okay? And on the y-axis here, we're going to have our pi term associated with our dependent variable, which is our drag force divided by density, width squared, velocity squared. Okay. And then from here, we're just going to simply plot the results. So let's say that we ran the experiment, we get data that looks like this. Okay. And then we're going to fit a curve onto that line. Okay. Okay. And then once you've run the experiment on your model, you can then extrapolate the results, in order to get the drag force on your prototype. Okay. Because remember, the dimensionless variables always have to be the same. Okay. So what we can say is that the drag force over rho W squared V squared, and this is for our full scale. Okay. This has to be equal to what we found in the experiment. Okay. So FDM over rho M W squared M, V squared M, okay? Right? And so this are from the experiment. Okay. And so what you can do is, in order to solve for the drag force on the full billboard, which is going to be this guy right here, okay? All you have to do is just to take your results from the experiment, your dimensionless variable, and then just multiply it by the conditions that you get, from the you expect from the full scale part. Okay. All right. And so this kind of shows you that, if as long as you match the dimensionless variables for your experiment, you can kind of scale it up and scale it down however much you need to in order to make it practical. And then from there, you can again use your dimensionless variables to extrapolate the results onto your full scale prototype. Okay. Right. Any final questions on this? Okay. So there's no more questions. That's all we got time for. So I know we went a couple minutes over, so I apologize for that. But again, so this is it for the dimensionless analysis. And so on Monday of next week, we're going to start up our next unit, which is on pipe flow. Okay. And so remember, Wednesday's a holiday, so we're not going to have lecture on Wednesday. And so next time I see you guys will be on Monday. So it seems weird to say this on a Monday, but hope everyone has a good rest of the week, has a good weekend. Have a good rest of your day, and I'll see you guys on Monday.
Thanks, Dr. Tran.
Thanks, guys.
Enjoy your weekend too, Professor. Thanks again.
You too.
Professor, can you hear me?
Yep. Mm-hmm.
I have a question on your color coding for the last part.
Yep. Mm-hmm.
I noticed that you circled for the full scale and then you just pointed up to the top numerator of the experiment. I wasn't sure what that meant.
Sure. So remember, what we're looking for here is the drag force FD on the full scale. And so that's kind of what I've circled in the numerator right here. I'll circle in purple. Okay. But the problem is, to run an experiment on the full scale conditions requires you to have basically a wind tunnel that's, at least 20 feet by 35 feet, because that's how big our billboard is. And so that's not practical. And so what is practical is to run an experiment on a billboard that's only 5 feet high and 8.75 feet across. And so if we run the experiments on that one, the way that we can extrapolate those results to the full scale model is that we have to take, this non-dimensional quantity here, this FDM, rho m, WM squared, VM squared. And so that's from the experiment. And then what we need to do is we need to multiply that by the full scale conditions. So we need to multiply by the density of the full scale conditions, the width of the full scale. And so that's going to be, 35 feet squared. And then the velocity of the full scale experiment. So that's going to be 10 miles per hour to 60 miles per hour. And so you're just multiplying basically by the conditions of the full scale in order to get the drag force on the full scale model.
Oh, you're just isolating FD on the left side?
Exactly. Yes. Yeah.
Okay. Thank you.
Mm-hmm.
Professor, I have a question.
Sure. What's up?
Can you explain again how you got pi 3? So on the previous example where you had you're solving for 3 pi terms.
Yes. Mm-hmm. Yes.
The h over w.
Yes. Yeah. So so that one I solved for. We call that by inspection. And so
Okay.
in the case where you have a relatively simple non-repeating variable, and so in this case our last non-repeating variable was this h right here, right?
Yeah.
And so since this h just has a dimensions of length, we say that in order to make this dimensionless, we just need to cancel this out with another length. And so if we look at our list of repeating variables, we see that we have w, which is also length. And so if we just kind of divide these two, then that gives us our third pi term. Yeah.
Got it. Okay. All right. Thank you.
Yep. Mm-hmm.
All right, have a good day, please.
You too.
Yeah. Professor?
Yep. Mm-hmm.
I was just wondering on the topic of dimensionless groups with experimental data.
Mm-hmm.
What was the point of having like the F naught and every other term?
Oh, you mean this guy right here?
Yeah.
Yeah. So this the point of this was to basically say that you want to we have this relationship here. So we have that basically, because we have one dimensionless variable, this ratio of the drag force divided by the velocity times the viscosity times the diameter, this one has to be a constant. So no matter what kind of configuration, so we can have, you know, a tiny sphere and a fast velocity, or we can have a big sphere and a small velocity. So this figure that I've drawn here can be applicable to, you know, a sphere of any size and a flow of any speed and any viscosity. And so this this F naught over D naught V naught mu naught, you can kind of think of this as the result of just one experiment that we ran. So let's say that we have a sphere that's like, you know, a certain size, and we ran the experiment on it and we found the drag force on it. So we can basically solve for what this constant is, this C, okay? And so what we can do now is we can take these results and kind of extrapolate to any sphere. So let's say that we have a much smaller sphere, let's say like a grain of sand, or a huge sphere, you know, I can't even think of one, maybe like a statue that's a big spherical thing. And so we can take the results of our experiment on this sphere and then kind of use those results to find out the drag force on any sphere under a flow. And so the way we did that is, you know, this F naught, D naught, V naught, mu naught, this is the results from one experiment. And so let's say like this is an experiment that you ran in your garage or something like that. And so you can take those experimental results and then you can, you know, apply that to any other situation. So this, what I said was that, you know, now that we know what C is, we can plug in for C over here. And then these conditions right here will be any other conditions. Right. And so this could be like for a small sphere, big sphere, anything like that. But basically what we're doing is we're using our experimental results on our handheld sphere, the one we ran in our garage, to get the results for any other sphere imaginable.
Okay, thank you.
Yep. Mm-hmm. Right. Are there any other questions? Okay. If not, I'm going to close the call. So have a great rest of your week. Have a great weekend, and I'll see you on Monday.